Okay, so I want to take a quick look at a sample P1 style question. So in this shape, I've got four forces acting on my object. I've got F1, F2, F3, and F4. So F1 is 80 newtons, F2 is 74 newtons, F3 is 26 newtons, F4 is 46 newtons, and each of them have an angle beside them. So the way I would start this question is first of all to break everything down by putting it into the table and then looking for a force vertical and force horizontal. What I mean by force vertical and force horizontal is if we have a force that looks something like this at a degree theta, that force is made up of a force vertical and a force horizontal. So to get to that same point of force, we could go straight along that angle theta, or we could come horizontally and up vertically. So I'm going to create a table, pause my video, and fill it in and explain it to you guys. Okay, so first of all, create a table like this and fill in your values for each. So F1 we said was 80 newtons, so 80. Our angle is 41 degrees, and we're given all that information when we draw our shape for the first time. F2 is 74 and 26 degrees, and we fill that in. Okay, so I've filled the rest of that table in just very quickly. Now, to get the horizontal and vertical components for each, we have a formula. Our horizontals is always going to be F by the cosine of theta. Our verticals are always going to be F sine theta. So fill in the formulas down both sides of your table there, and we'll finish off the question together. Okay, so we can get this far just by using the formula. All we're taking is F, our F value, 80, the cosine of the angle, and F sine cosine. Sorry, F sine theta, the angle again. So you get that far, you plug them into your calculator and you get values. So again, I'm just going to pause the video here and fill my values in. All I'm doing is plugging each of these formulas into my calculator exactly as I see them and taking the values. Okay, so I'm going to do the top two on my calculator, pause the video and just fill these things in and stop and consider what I need to do next. So 80 cos 41 is going to give me 60.4. So I'll fill that in. So 60.4, 80 sine 41 is going to give me 52.5. So stop. I'm going to fill my table in. I'm going to talk a bit more about what the sine of each of these should be. Okay, so that's my table filled in. But I need to think of what the sine of each of these should be. And to figure that out, I can redraw my shape from the start of the question. Okay, so I've copied it. If you're doing this on pen and paper, you will have to redraw it. But before I remove my blue arrows, I can think about what way my force should move to get to that same point. So for this force, F1, I have to move to the right horizontally and up vertically to get to that same point. F2, I would have to go left horizontally and up vertically to get to that same point. F3, left horizontally and then down to get to that point. And F4, I would have to go to the right and I would have to go down to get to that same point. So I can erase my blue, hopefully. Might need to do a little bit of tidying. Should be okay overall. Okay, we're not too bad. Bit messy. So now, these are the equivalent directions of my forced horizontals and my forced verticals. At the very start of this question up here, I said any force traveling upwards, I'm going to take as positive. Anything coming down is going to be negative. So I need to look at F1 and I see, okay, it's going up vertically. It's going to the right horizontally. So it's going to go up, which is positive, and to the right, which is positive. So my horizontal and vertical force of F1 is going to be positive. That's a bit big. So positive and positive. F2 then. So it was that 74 Newton force. I said to get to that same point, I would have to travel left and up, as shown here. So I have to go left and up. Left is negative, so my force horizontal is going to be negative. My force vertical, I'm still going up. That's still positive. And I consider this for each of them. My force 3, horizontal and vertical, I'm going left. I'm going down over here. So both of these are going to be negative. And my force 4 here, I'm going to the right horizontally. So I'm traveling positive in the horizontal, but I'm going down vertically. So I'm going negative in the vertical. So now all I do is I get the sum of these horizontals and verticals, and that lets me find the resultant. Okay, so I've actually tidied my drawing down there at the bottom left. A little bit of mess was annoying me, but I want to get the sum of my horizontal and vertical forces. So start horizontal. We have 60.4 minus 66.5 minus 8.5 plus 37.7. So for this question, my force horizontal 1 and 4 are positive, 2 and 3 are negative. When I add all those up together, I get 23.1, and my unit would be Newton. I do the exact same thing for my force vertical. To get the sum of my force vertical, I add up all the blue values here, including the sign. So it's 52.5 plus 32.4 minus 24.6 minus 26.4. That should give me 33.9 newtons. Now, what this tells me, first of all, that both of these things are positive. So if it's positive, my horizontal is traveling to the right with 23.1 newtons of force. Vertically, it's positive again, so it's traveling up of 33.9. So I can add these vectors by joining them together like this. And I can find the resultant of the force. So all the resultant means is if we add all of those forces together, what would actually happen is it would move at this angle theta with magnitude r. So r is found using Pythagoras' theorem. It's going to be equal to the square root of the other two sides squared. So 23.1 squared plus 33.9 squared. You stick that into your calculator and you see what it works out as. Okay, so hopefully you guys can plug that into your calculator and you're going to get 41.0. So 41 newtons. So know that our value is actually 41 newtons. So all of those forces, if we were adding them together, we know that this shape is actually going to move in that direction, or with a magnitude of 41. To find the direction, theta, it's going to be the tan inverse opposite over adjacent. So remember, if this is your angle theta, opposite of this is 33.9, adjacent is 23.1. So you might need to go over your trigonometry to remember that. So opposite over A, opposite over adjacent, it's going to be tan inverse of 33.9 over 23.1, which should work out to be 55.5 degrees. Yeah. Might be a small error in there due to random, but it's fine for the purpose of showing us what we're doing. So we can get rid of theta. And there we can say in reality, this shape is moving with a magnitude of 41 newtons at an angle of 55.5 degrees. Okay, now our question asks us to find the distance that resultant acts from the point A. So before now we didn't really need to consider our point A, but we're told our point A is here where force F1 starts. So now we're going to go on to looking at moments to solve this question and find that distance. So what do we need to know about moments? We need to remember that a moment is equal to a force by perpendicular distance. And we're going to take our moments clockwise to be positive and moments counterclockwise to be negative. So your next step should be to fill in your values for each of your vertical and horizontal components onto this diagram. Okay, so I'm going to pause my video here. All I'm doing is I'm taking my force horizontal and my force vertical components and putting them onto this diagram. So for example, force horizontal of F1 is 60.4 newtons. Force horizontal of F1, force vertical of F1 is 52.5 newtons. So I'm just going to pause the video. I'm just filling that in the whole way down. Okay, so I've finished adding those drawings in. Just going to move these calculations out of the way. Move them up here briefly. And we can always come back to them if we need them. So I've got all of my force vertical and force horizontal components in, labeled on my diagram. What I would do now again is I would create another table and calculate the moment each of these forces is creating about the object. So create another table. I'm going to create the table again now by pausing the video. And first of all, fill in what we know. Okay, so create a table of all your forces. Remember, each force is going to break down into horizontal and vertical component. So each of these horizontal and vertical components are going to have separate moments. The key thing to remember here is that moment is force by perpendicular distance. So when we're looking at all these horizontal forces, so to explain this a little bit better, F1, my horizontal is 60.4. My perpendicular distance, well, there's no perpendicular distance to that point A in this case, so it's going to equal 0, and those going to equal 0. Similarly, vertically, it's going to equal 0. So picked a bad example to start off on there, but if I look at F2, ignore the sign. So the sign's only going to come from a clockwise or counterclockwise moment. My moment is my force distance. So my force is 66.5 by, you might think your distance is 4. That's a horizontal distance. You want a perpendicular distance. 66.5 by 5. With your calculator, and it's going to be 332. Is it going to be positive or negative? Well, let's take a look and have a think about it. If I only had this shape. It was pinned here. So if I only had that shape, it was pinned there, and the only force that was acting on it was that horizontal. So if I pushed in here, the object would rotate around this point this way, which is clockwise. So that's going to be positive. So I'm going to pause and fill in the video. Have a look. See, do you understand the distances, and do you understand why things are negative and positive? It all relates to if you isolated that force, looked at it by itself, and pushed or pulled on this shape, is it going to spin it clockwise or counterclockwise about this point A? Okay, so I've put in my force and my distances. I just want to make a point of putting in the signs of my moments. So F2, if I look at force vertical of F2, it is here. So if there was no other force acting on this shape, it was nailed into the wall at A, and I pull it at F2 in this direction. It's going to make the shape twist this way, which is counterclockwise around A. So this is going to be a negative moment. It's going to be minus. And our moment in this case works out to be 129.6. And you can do that for all when you're trying to consider the sign. So to 8.5 times 5, F3, that's here. If that was the only force acting on my object, I'm pinned to the wall at A, this is going to make my object twist clockwise, so that's going to be a positive moment. Positive. F3 vertically. It would come down here like this. If that was the only object that was happening, it would make my so it would make the shape rotate counterclockwise. It would go counterclockwise around that point A. So here it's going to be negative F4 horizontal. Again, I can eliminate every other force on my shape and consider F4 by itself. F4 horizontal is here. I want to ignore everything else that was going on previously. So if that was my shape, I'm pinned to the wall at A. That would make this object want to twist this way, counterclockwise again. So F4 is going to do a negative horizontal moment. And F4 vertical. So F4 vertical. I have a force. It's 26.4 newtons. I need to have a horizontal distance between it and A. So I need a perpendicular distance. There is none. So there's going to be no twisting. So if this object was pinned to the wall at A, let's redraw my object very quickly. If I was pinned into the wall at A, and I'd have a force pulling it down here, there wouldn't be any twist. There's no distance in there, so that's going to be equal to 0. So now I get the sum of my moments horizontally, my moments vertically. Then I get the sum of my moments by adding both of these together. So I'm just going to do that very quick. Fill in my table and calculate the sum of all my moments. Okay. So my moments horizontal work out to be 33.9. My moments vertical are minus 252.6 newton meters. I add both of these together, and the sum of my total moments in this shape is minus 218.7 newton meters. But what does that mean? Well, if we know we have a negative moment and we know our resultant, we could eliminate all of the forces and say, well, what is happening is somewhere on this shape, our resultant, which we calculated up here, ignore that line, our resultant, or 41 newtons, acts somewhere on this shape and causes it to spin counterclockwise with 208.7 Newton meters of force. If we want to calculate the distance or where exactly that error is happening, we can use the moment formula. So remember, a moment equals force by distance. We're eliminating all the forces. We know our total moments. We know what R would be, the equivalent of all of those forces broken down into vertical and horizontal components. And we can say that 218.7 is equal to 41 times D. D equals 218.7 divided by 41. D equals 5.3. So 5.3 meters away from A is where this force acts. Now consider R acts in this direction. So it goes in this sort of shape. If it acted to the left of A, it would actually push the object clockwise. So it can't be that direction. It has to be to the right hand side. So we know perpendicularly R acts somewhere about there, which is, this isn't drawn to scale, 5.3 meters away. So everything that's been going on in that system that we started out with up here, everything that's happening in there can be replaced with one line, and that line is R. If we want to keep this in equilibrium, we need a shape or a force, sorry, that's going to give us an opposite reaction called our equilibriant. That's going to be E, equal but opposite to R, and it's going to keep us in equilibrium. And that's us. We've finished the question. So there's a couple of steps in there, and there's a few key things to get your head around. But hopefully that made sense to you guys.